Last session, we were working on protocols. And if you recall, the protocol is the air interface between the reader and a tag. And an example of a protocol is how we write a letter. We use certain letters, snail mail. We use certain letters. We put those letters together to form words. We put the words together to form sentences. We put the sentences together to form a paragraph. We put paragraphs together to form the complete communication that we want to give. We then put that in an envelope, and in the envelope, we have to put who it's going to in the center of the envelope, and we put who it's coming from at the top left. We put a stamp at the top right, and we post it. Now, all of that is a protocol. How do you write a letter? How do you send the letter? And so, so that's an example of a protocol. So what we're talking about here is how does the tag communicate with the reader? How do they exchange data? How do they, as we're going to find out more today, how do they isolate a tag? How do they handle multiple tags? How do they do how do the reader and the tags interface with each other? And that's what we're going to talk about today. Getting through with that, then we'll talk a little bit about RF physics. And today, it's going to be the most technical of all of the presentations. So it's a good review to get an idea, because it's going to be covered more in more detail in the class session. But going back, reviewing a couple of slides, if you recall from last meeting, when the reader is reading a tag, it has multiple tags out in the field. You have a case with, say, 50 tags on it. And so the first thing it has to do, the reader has to do, is go out and select which of those 50 tags it's going to read. For example, if we had personnel tags or badges with personnel and we had inventory tags, if it's going through a portal, we only want to read the inventory tags. We don't want to read the personnel badges. So, there obviously is some way of identifying the difference on the tag between a person and a piece of inventory. But anyway, so the first thing the reader does is it selects, in this case, just the inventory tags. After it selects those inventory tags, then it goes through a step that we call inventory, in which, okay, now I've selected these 50 tags, and it identifies which ones it's going to read, and then specifically determines and identifies a specific tag, because remember, a reader can only read one tag at a time. So it has to isolate a tag, get it down to one tag, and this process is called anti-collision. So now that it has one tag, then it can go ahead and access that tag, read that tag, write that tag, do what it's going to do it. Then it does what we call puts the tag to sleep, and then it goes back to get another tag. So it goes through this process every time it reads every tag. So first it has to select out of all the tags that it's reading, which one does it want to work with. Then of those, it does an inventory and says, okay, here are all the ones I want to read. And then out of that, it picks one tag, selects one tag, and then does the access to it. So that's the process that it goes through. And that process of isolating one tag and working with one tag, once again, is called anti-collision. And this is just the process that it goes through to do all of those things. The first part is doing the isolating the tag, and then it is actually getting the tag and reading the tag. So this is the inventory and access process. We also talked last time about channel hopping. In the United States, we have 50 channels, the bandwidth from 902 megahertz up to 928 megahertz. And we've divided that into 500 kilohertz channels. So we have 50 channels in the United States. So when a reader goes to work on a channel, it does what's called listen before talk on that channel. If it hears something on that channel, then it will skip over to another or hop over to another channel and keep doing that process until it finds a channel that is available. and then it uses that channel for communication. Listen before talk is an important feature and was set up primarily to cover EU and Europe, because Europe only has 10 channels, 10 workable channels within their frequency range for UHF. Once again, everything we're talking about today is UHF, ultra high frequency, 860 to 960 megahertz. All right, so that's channel hopping. Now, once again, if you have any questions as we go through here, ask them. If for whatever reason you're muted, just unmute yourself and ask the question. Once again, some of these are going to get more technical as we go through the process. So anti-collision is the process by which the reader isolates a single tag out of a group of multiple tags that are in the read zone at the same time. The reader can only read one tag at a time, so it has to isolate the tag and come up with just one tag. And so we're dealing with ISO 18006C, if you recall that, class 1 Gen 2, but ISO 18006 used the binary tree. 18006B used a process called Aloha. But what is important to us, certainly for the course and the exam, is that the ISO 18006C uses the Q factor as the means for isolating a tag. So I'm going to walk through that process right now, and so ask any questions once again if you're having confusion. So with the Q factor, yeah.
Jim, this is Archit here. Can you hit the hide button on the pop-up for go to meeting?
I tell me where to go to do that. I don't see it anywhere.
It's on the slide. Yes, right there. If you can hit that hide. Thank you very much.
Thank you. So with the Q factor, what happens is that the reader sends out a command to the tag, and it tells the tag to generate two random numbers. One will be a random number up to Q to the 15th, which is 64,000. And if the reader decides that that is the tag it's going to work with, then that binary number becomes the tag's handle or its name. In other words, so once I isolate a tag, I need to be able to identify that tag and tell that tag to send data. So the first number that the reader sends out a query command, a Q command, to the tag. It tells the tag generate two random numbers. The first random number will be Q to the 15th, which is 64,000. And that will be the individual tag's name if they use that tag. The second random number that the tag is going to generate will be based upon the reader. When it sends out its query command, it puts out a value, 2, 3, 4, 5, up to 15. And in that process, when the tag gets that number, it uses that number as a power of 2. For example, if it's a 3, it'll be 2 to the 8th. 2 to the cubed is 8. And that tells the tag to generate a random number between 0 and 7, since 0 is a valid number. Okay, so now the tag has generated two random numbers, and now all the tags have. And now the reader sends out a command to all the tags that the tag reads, and it says, does anybody have a 0 in the leftmost position? Okay, so remember, it generated a random number 2 to the 8th in this case, since we sent a Q value of 3. Does anybody have a 0 in the first position, at the leftmost position? If the answer is yes, then and only if no tags respond, because then it will say, okay, subtract 1 from your random number. And now does anybody have a 0 in the high order leftmost position of the binary number? If it gets a response of, and only one response from one tag, then it says, okay, you're the tag that I'm going to work with. What is your handle? What is your name? What is the other random number that you generated? The tag sends that random number to the reader, and now the reader has established and isolated, singulated a single tag. And now it will access that tag and do whatever it's going to do, read data, write data. Okay? So then it goes back and it will send out, says, okay, now I'm done with this tag. Now I'm going to send out a new query command, and based upon how it puts that tag to sleep, which we'll talk about in a minute, then all the other tags will respond, generate 2 random numbers, and it goes through the same process one at a time until it gets no response coming back from any of the tags. All right, so that's how it isolates it. It's called the Q factor. All right. Any questions on that? The silence is deafening out there, guys.
Yes, Gert here. I have a question.
Yes.
If there are a high number of tags in the interrogation zone, then it could very well be that there are 2 the same random numbers.
It is possible.
Impossible. Yeah.
No, that's possible. Well, if there are 2 tags that have the same random number, then when it looks at the high order position, it's going to get 2 responses. So it's going to say, hey, I've got 2 responses. I can't deal with one of you. So it sends out a query command. So in the example we had, it sent out a Q to 3 as the value for 3. So if it has 2 with the same number, then it's going to get 2 responses and says, I can't deal with you. So it will send out the query command again, and this time it will add 1 to the 3. So it'll say, okay, all of you generate a random number between Q to the 4th, which take the power of 4 to the 4, which is, so all of you now generate a random number between 0 and 15. And then it checks again, high order position. Is anybody have a 0 in the first position? If it gets more than 1 response, then it will go back and say, okay, I'm going to send out another query command. This time I'll up it to Q to the 5th, which will give me 1 to the 32nd, or between 0 and 31. Okay, so it keeps doing that and incrementing the Q value. So the Q value is the number, the power of 2, that tells you what range you're going to have to generate your random number. So if they have the same number in your case, then they're going to be identical when it examines to say, do any of you have a 0 in the first position? When it gets more than 1 response, then it says, okay, I'm going to send out another Q value, which will be 1 more than the previous Q value. Does that make sense?
Yeah, okay. So typically it will start with a low Q factor, and if you have a high number of tags, it will increase.
Right.
Yep.
And so typically there's a general rule of thumb that you can specify the starting Q value. And as a general rule of thumb, you want to start the Q value that will give you 2.5 times the maximum number of tags you expect to see in the read zone. So if you expect to have 20 tags, then you want to set a Q value that's going to be 64, which will be Q to the, 6th? 2, 4, 8, 16, 2, 4, 8, 16, 32. So yeah. So if you're going to expect to have the maximum number of tags you're going to have is 20, then the initial Q value would be set at Q to the 6th, which means you're going to start out at 64, generate a random number between 0 and 63. Okay.
That completely clear. Thanks.
Okay. Now the good news also on this is that virtually all of the readers that are on the market today automatically sense how many tags are in the field and automatically set the appropriate Q value. But if you have some of the older readers, you have the option to go in and actually set the Q value itself. Okay. Okay. So, and the next couple of slides, I'll just put it here so that if you go do the review this, you'll be able to see it and review it. Just go over what I was just discussing. The key takeaway from here is that the Q factor is a number, and it's the number which is represents a power of 2, and it tells the tag to generate a random number using that as the Q factor power of 2 as the maximum number to generate. Once again, if it's a Q to the second, then you're going to generate a random number between 0 and 3. If it's Q to the third, you'll generate a random number 2 to the 7th, etc. Okay? Okay, so the next feature we're going to talk about, we're changing subjects on you, is that within the UHF ISO 18006C Class 1 Gen 2 protocols, we have what are called sessions. Now, a reader can only work with one tag at a time, as we just found out. However, a tag can work with up to 4 different readers at the same time. So physically built into the silicon on the chip itself are what are called sessions. And there are 4 sessions. Now, when a reader sends out a read command, it sends out what session it wants to read on the tag. So it would say, I want to read session 0. Now, when it goes through the process, and now it's gone through the isolation, and now it's down to reading that tag, and it says, okay, I'm going to access that tag, then the tag itself has in each of the sessions, has a switch, an A and a B switch. Think of it as A as I'm available and B, I'm busy. So all the sessions are available. Once the reader connects to a tag on a given session, then that A-B switch switches over to B, which is busy. So now that particular session is tied to that particular reader. And if another reader tried to read that tag, it couldn't. All right, and that tag stays busy until the reader disconnects from that tag. Okay, and so that way, if you're doing you have 2 different processes going on. You want to be able to do let's say you had a smart shelf. A smart shelf is where you have it like in a pharmaceutical cabinet, where you have all the drugs have tags on them, and you have on the shelves you have readers. You're reading the tags all the time, and if somebody removes one of the containers, you know that container was removed. So that's a smart shelf application. So if you're doing that application, and now you want to come in and with a handheld, you want to do an inventory on those same tags that are already being read. And on a smart shelf, they would be in session 0, and we'll explain why in a minute. So they'll be reading session 0. So when you come in with a handheld and you want to do an inventory of what's in that cabinet, you can do it with a handheld, and you tell the handheld to read on session 1, 2, or 3. Okay, so that's where and how and why you'd want to be able to use different sessions or for accessing a given tag. So once again, a reader can only read one tag at a time. A tag can have up to 4 readers connected to it, each on a different session, because the tag itself on the silicon is built in to have 4 separate sessions. All right. Now, what happens here is that each of these sessions has when you connect into one of these switches, if you connect on session 0, then you have the reader is connected to that tag. Once the reader stops communication, says I'm done, then the busy switch automatically reverts back to A immediately. All right, so that this is how we do continuous reads. so that it's active. It goes busy. When you're done with busy, it drops back to active immediately. All right. Now on session, if you connect on session 01, then you're going to read the same way. It's going to flip to busy. When you disconnect from it, it's going to stay in the busy state for up to about 5 seconds, depending on how much power that the tag can hold on to, but up to about 5 seconds, so that during those 5 seconds, nobody else can read that tag on that particular session. All right. If you're reading on session 3, then you're looking at staying in the busy state for up to a minute, once again, depending upon how much power the tag can hold. And also in session, so in session 2 and 3, it will stay in the busy state for up to a minute. Now, when do you think you'd want to make a difference between session 0 and session 1 or 2? So we talked about a smart shelf. A smart shelf you're going to want to read on session 0 because you're going to want to continually read it. And after you're done reading it, you want to read it again because you want to know the moment that it would be removed from the shelf. All right. Now, if you have a pallet going through with 20 cases on it, if you, for whatever reason, you told it to read on session 0, it's going to read a tag. It's going to put it back to be available again. Now, going back to our earlier slide where it's doing the select the inventory, and during the inventory process, it's trying to use the Q factor to find a isolated tag. If a tag is read and then it goes back immediately available again, theoretically, the reader could read the same tag 20 times as it's going through the portal, because it's always available. I'm available, I read it, and then I stop reading it, but the tag's available immediately. So are you available? So theoretically, following the Q factor, a reader could read the same tag 20 times and never read any of the other tags. So in that case, we would want to use a session that's on, say, session 1, where once we read the tag, it stays busy for up to 5 seconds. So during that 5 seconds, that tag session is in effect put to sleep, and it's not available to be read, which will allow the reader now to read all of the different boxes. The same thing is true if you had a lot of boxes and it's going to take you more than 3-4 seconds to transit the read zone, then you'd go ahead and read on session 2 or 3, which means that tag is going to get put once you've read it, it gets put to sleep, and it's going to stay in the busy state for up to a minute, which means you'll have an opportunity to read all the tags. Okay, that makes sense? Any questions on that? And once again, we'll go over this again during the class. And so, all right, okay. And just an aside, on Thursday morning or Thursday afternoon, excuse me, of the session, we have a benchmarking class. And so if based on what you've signed up for, we will be showing demos on all of this on sessions and how they work and mapping, so you can see what the difference is and how they read tags and all the rest, so you can see actual working on this. Okay, now the next concept we want to talk about is what's called dense reader mode. Once again, we're still talking about protocols. We're talking about the protocol for UHF, ultra high frequency, 860 to 960 megahertz. Now, a dense reader mode, by definition, is when you have more readers in a 1 kilometer area than you have channels available, then you have a dense reader mode. So what that means is that if in the United States, we have 50 channels. And if we only have 1 reader, then that's no problem because it'll always find a channel. If we have multiple readers, but less than 50 readers, then there will always be a channel available. And through channel hopping, it will be able to find a channel on which to communicate. If we had 60 readers within a 1 kilometer area, and the reason it's 1 kilometer is that a signal at full power from a reader can be discerned add up to 1 kilometer. All right. That's why it's 1 kilometer. So if we had 50, 60, 70 readers, then it's possible that all of the readers, all the channels could be tied up. So a reader comes in and says, I want to read, and it hops around, but all the channels are busy. So what does it do? So in the protocol, they implemented what's called dense reader mode, in which case the reader must guarantee that each channel, each reader will have access to a channel in no more than 0.04 seconds. And there are various different techniques for the reader manufacturers, the vendors, to do this. So they all do it potentially differently, but the basic rule is that if you have dense reader mode, then the reader has to be able to identify and have a free channel available for a reader within 0.04 seconds. All right. Now, in the United States, this is not as much of an issue as it is in Europe. Once again, Europe, EU only has 10 workable channels. So dense reader mode for Europe would be if you have more than 10 readers within a 1 kilometer area, which is highly likely if you're dealing with any kind of a warehouse or multiple readers, even within your own facility. So, but that's why dense reader mode was developed. Once again, this is automatic within the readers. If you have some old readers, you may have to turn dense reader mode on, but with the newer readers, they are automatic with a dense reader mode. But it's important to understand what it is and how it works. Okay. We'd seen this slide before that shows that each area within the world chose its own frequency range within the 860 to 960 range. So that's why we have a range for UHF ultra high frequency ISO 18006C. And I know that sounds boring, but it's important for you to know that. ISO 18006C has a frequency range of 860 megahertz to 960 megahertz. And this is just where some of the channels are, channel ranges are for the different countries. And you can go out to GS1 website and they will show you all the countries and what the frequency ranges are for all the different countries. This is important when you're buying the equipment or the RFID readers, that you get a reader that has the correct frequency range and power, which we're going to talk about, for your particular region, or you buy a universal, a reader that is identified as a universal reader, which will go anywhere in the world, or buy one specifically for the US or EU or whatever country you're working with. So this, we talked about.
I have a question.
Yes.
You say there are 10 channels in Europe. I remember
Yes.
a graph with the power on these channels. Is it true that not all these channels have the same amount of power allowed? So that it's maybe even less than 10? So the channels on the side of the frequency, I remember they have maybe half a wattage of power allowed.
Correct.
Or is it not true?
No, you're absolutely correct. So the total number of channels available in Europe is 15. But
Yes.
because as you said, 5 of them are very reduced power, 2 at half watt. So they really are not very usable. And so that's when we say we have 10 usable channels within Europe. There are 15 total, but the power level, as you correctly stated, on some of them is a half a watt. On others of them, it's a 1 watt. So since there is not enough power to give you a very good read range. So consequently, those 5 channels, 5 of those 15 are not practical or usable, and that's why we have 10 usable channels.
Okay, yeah, thank you.
Not sure. So we talked about tag data selection, dense reader mode. sessions, variable data rates. The other thing that we have, which we had talked about earlier, is that we have from a security point of view, the Class 1 Gen 2 ISO 18006C, and I know that's boring, but it's important for you to remember that, has as one of its capabilities is the ability to kill a tag so it cannot be read again, and or to put an access password on it so that you have to have a password on it to be able to access it. And one of the labs in the class will go through killing a tag and setting up access passwords and how that all works. So we'll have a lab on that in the class. This is just an example, shows the number of channels available for different areas. And once again, as you mentioned, under Europe, it says 10 to 15. 10 are usable, there are total 15 for some different countries. But if you want to see what this total thing is, then you can go out to GS1. And the other thing, just a refresher, is in the United States, we use a unit of measure that's called a EIRP, effective isotropic radiated power, which means we use a theoretical antenna and isotropic antenna for doing our calculations of power. And in Europe, they use what's called ERP, effective radiated power, in which they use a dipole antenna for doing the calculations. Okay, so you'll see 2 watts of ERP versus 4 watts of EIRP. And if you want to convert EIRP to ERP to EIRP, you'd multiply it by 1.64. So, okay, so that's the difference between the powers that you're looking at there. Okay. Once again, we can lock the memory.
Sorry, a question on the previous sheet. Why is it set varied in New Zealand for a number of channels?
It's what, once again, when UHF was set out, each of the countries had its place to be able to establish what frequencies it wanted to use. In some cases, if it chose frequencies that are very close to each other, when we looked at then you can always get bleed over from one channel to another channel. So as in Europe, 2 of the channels only have a half a watt of power, because if you put more than that, then you'd get bleed over or interference from those channels to whichever channels were next to them that were not part of RFID UHF. So consequently, they only allow a minimum amount of power, the 0.5 in this case. And so what New Zealand is saying is that they have power from 0.5 to 4 watts. And if you looked at the number of channels, it says very down at the bottom, because of the way they've set up how they want to handle UHF communications and how they want to set up their bandwidth and how they want to set up their channel usage. So that's why you'll see the different wattage. The same thing with Europe. We could have at Europe put in there. So they reduce the amount of power.
Looking at the band size, it could be 50, but they are not all usable, maybe because of the different wattage.
Exactly. Okay. Yeah. So we can protect the tags we can put an access password on the tags. Tag data can be encrypted before it's written to the tag. Okay, the chip on the tag is a memory chip, so you don't have any real processing capability. So you can encrypt the data before you put it on the tag. All right. Now, once you've set up the data on the tag, you've put in your EPC codes, your access codes, whatever, you can lock those codes so they can never be changed. And then you can also permanently kill the tag. And the way it kills a tag, which once again, you'll do this in a lab in the class, it'll just sets a bit in the tag memory. And when the reader reads the tag, it always checks that first bit. If that bit is set, then it automatically ignores that tag from going forward, and so as long as you're following, within the protocols, you'll never be able to read that tag again ever. It's a permanent kill. Okay, so that these are all part of Class 1 Gen 2 ISO 18006C protocols. Okay. Once again, the Class 1 Gen 2 is another name for it. GS1 and an organization within GS1 called EPC Global has set up the standards for UHF and got approval for the standards, and that standard was called Class 1 Gen 2. I don't know why it says Class 2 up on top. That's an error on the slide, but anyway, it should be Class 1 Gen 2. And then it has subsequently added V2, version 2. But the key thing here is that EPC Global, that's what so your EPC electronic product code class should be Class 1, sorry about that. Class 1 Gen 2 is the name of the standard that is equal to, that standard was then taken over and passed by ISO, so it became ISO 18006C. So EPC Class 1 Gen 2 is identical to ISO 18006C, just two different standard setting organizations and their numbering systems. Now, with an upgrade to Class 1 Gen 2 came out with V2 version 2, which adds some additional features as far as the untraceable function to hide portions of the data, support the cryptographic authentication of tags and readers. In other words, you can put a code that you can now use that to authenticate a given tag or reader. You have enhanced user memory. So now, if you're way back when we talked in the EPC Class 1 Gen 2 ISO 18006C standard protocol, we had an area for user memory, and that was in the fourth bank 03 of the tag. And in that memory, up until now, that memory was unorganized. You just wrote it and it was just a string of data. Within V2, you can now organize that data and have a file structure within that user data. And that's what that means, enhanced user memory. And non-removable is that you put the flag for tagging the data is sewn in a tag so that the tag cannot be easily removed. A feature, if you look at some of the price tags, when you look at things, you try to tear it off, and it'll only allow you to tear off part of the tag and not all the tag, and keep the tag in contact. So the V2 provides the capability that if you remove it, it will destroy or make it very hard to be able to read the tag if you removed it. Those are just additional features for version 2. Okay. Now, we have what's called a low-level reader protocol. Now remember, all these protocols, every reader and tag must have a protocol. They must be working on the same protocol to be able to communicate with each other. And up until LLRP came out, each reader and tag manufacturer had to write their own protocols, which meant that if you bought a reader from Alien, you had to buy tags from Alien. If you bought a reader from Zebra, you had to write a tag from Zebra. So the class EPC Global came up with a standard protocol that's called LLRP, Low-Level Reader Protocol. So within the protocol, LLRP, low level, just means it handles the low level of the communication, not that it's a low-level product. So LLRP came out that handles probably 90% of what's necessary to be able to do the interface to tag. Everything we talked about, sessions, dense reader mode, all that is all covered and handled in LLRP. Now, each reader or manufacturer builds some additional features within their particular products. And so each reader manufacturer, Alien, Zebra, Intermec, etc., will take LLRP as the base, and then they will add a few features that emphasize the use and capabilities of their equipment. So LLRP then becomes the base for everything, and then each of the user manufacturers will only have to add a few features to it. And that way, everything then becomes an open system in that we can use anybody's tags with anybody's readers. So LLRP is a very important feature that's part of the Class 1 Gen 2 UHF ISO 18006C protocol. Okay, and if any of you missed that on the test, I'm going to hit you. Okay, ISO 18000 Class C. All right. Class 1 Gen 2.
So quick clarification that EPC Gen 2 was a protocol defined by EPC Global, which eventually got GS1. Some of the names like Zebra and others were actually not there. They are recent names who acquired the company who were there at that point of time. And LLRP was subsequently developed to have a common protocol between an application and the hardware, so that any company who is actually embedding EPC Global Class 1 Gen 2 should be able to actually have a standardized driver function for all these hardware readers, just like your VGA monitors, which used to be there, or mouses, which has a generic driver in Microsoft system. So just a clarification that LLRP was defined to have a low-level reader interface between an application and the thing to adopt the EPC Global Class 1 Gen 2, and now there is a new protocol, Class 1 Gen 2 V2.
Perfect, thank you. Okay, so once again, the slides are there so that when you look at this or play it back, you'll be able to see them that was just discussed. Okay, the other next very critical feature is what's called a middleware. And middleware is, so you have your data flow structures on how data flows, and then you have, so the data is transferring, for example, all the data is represented in binary when it's written to the tag. And when it goes through your communications through the air, it's all binary, it's all zeros and ones. So, and then we use a system called hexadecimal to be able to represent that data in a different form. And then we have to encode that data into a specific form for a given tag. So your data flows, once again, I'll walk through these and you take a look at them when you review the deck, but it just shows the format of the data from input sensors to when you read it to how it gets written into your databases, etc. So it just shows you what the format of that data is. And once again, whether it's hexadecimal or XML or binary. Okay. Then you have the decoding of data. If you look at barcodes on products, that barcode has a specific structure, and that structure contains specific information. And so we also, when we write data into the tag, we use a given format or structure for representing the data and what it looks like and how it looks. We'll go into much more detail on this during the class, but understand that the data can be written through form, but also there's a structure. So if you're going to do DoD or the automotive industry, there's a given structure in which what data has to appear and how it's formatted. That's how, just on the encoding. So once again, Walmart, AIG, DoD, all have their own mandates, all of which use UHF Class 1 Gen 2. Okay. The data format, yeah, for the EPC code that's stored. If you're using the GID identifier, which is one of the formats that you could use, there are many different ones, but you have a header, you have the company name, you have the product EPC code or SKU, storekeeping unit, or inventory item number, and then you have the serial number. So all of this will go through in much more detail. It shows an example of one. Of what it looks like for the GID, the 96-bit. So we can identify every item, case, pallet, etc. The middleware is important. Middleware has 3 levels. The lowest level of the middleware handles the equivalent of the drivers. You can't put a printer on your system without loading the printer driver or any device. So the same thing here, all of your different devices have different drivers for them. And those drivers all have to be set up and configured for use. And middleware handles that. So that once the data comes out of middleware, the system doesn't know how the data got there. So the lowest level can have any devices. You can have handheld readers, you can have RFID readers, you can have HF readers, LF readers, all whatever you want. And your drivers at the lowest level of the middleware handle all the protocols to be able to read and write the data from that. From there, now the data is in a position where it needs to be filtered. So you only get the data that you want written into your database. Has to be aggregated. For example, if you have a purchase order system, line 1 on the purchase order says 100 items. And in today's system, your receiving systems, accounts payable systems are going to look for line 1, 100 items, line 2, 200 items, which is what gets entered today. When you go to RFID, you're going to have 100 reads. So you can't send 100 individual reads up to your payable system, up to your receiving system. So therefore, we have to aggregate the data that says, yeah, we read 100 tags, but that equates to line 1, audio number 5, and that's 100. And so we send the 100 up. So we have to do aggregation in the middleware, and we also have to apply business rules. Business rules are simply looking at the data, saying, oh, this inventory number, this is a valid inventory. It's not an inventory number. Oh, this is a book versus this is a pad of paper versus this is a pair of scissors. So the business rules will go through and do the identification of what that data is so that it gets categorized properly when you pass it up to the system. So the next level of middleware does those functions. And then then that data goes into your operating systems that now can work on all that data. What do we have? Where to go? Which eventually gets up into your standard ERP systems, your receive and your inventory control and all the rest. So the middleware is absolutely critical, is absolutely necessary. You cannot run RFID without middleware in some form that handles the drivers, that handles the translation aggregation of that data, and then formats the data correctly to be passed into your various different ERP systems. So the short version on middleware. Okay, so the next several slides just go through and talk about what we just talked about once again, so you can look at it in the review and see what's there. The middleware functions, once again, supports your read-write devices, your event data management. Each time the reader reads a tag, that's called an event. Or each time an electronic eye sends a signal, that's called an event. So you have the event management, cleaning up. Remember that data is in binary, so it has to be cleaned. It has to be changed to a different format, all of that. EPC, electronic product code handling, this is the data that's in the tag itself. What event recognition, what event was it? Was this a tag read? Was this an electronic eye, etc.? Task management, what are you going to do? Put the logic to it, and then buffer the IO. An aside at this point in time is that none of the RFID readers have data storage in them per se. Unless you're dealing with a handheld or some processor, but your standard readers don't have memory. So the data comes in, it gets read into a buffer, it needs to be sent from that buffer up through your middleware into your applications. If it's reading too many tags and that buffer fills up, or there are difficulties in transmitting the data because the network's down or something like that, the reader keeps reading data and filling that buffer, and the data just falls out of that buffer into the bit bucket. So you will lose that data. So it's critical that whatever you're doing, you're reading the data from the RFID reader, that you get it passed into your middleware, as quickly as possible, because the reader does not store data. It only has a buffer in which it loads as it's reading. Once that buffer is full, it will keep reading, and the data just falls, and you lose the data. Embedded versus host. From an application point of view, we have the ability to put embedded applications on some of the RFID readers. Not all RFID readers have that capability, so when you're looking at your readers, you'll have to look at the reader to decide whether it will handle embedded code on that reader. Now, we're not talking about handhelds, because that basically is a computer with a reader, but your basic readers can handle and work on applications that work on data directly that's on the tag, from the tag. When you're working with embedded code, the embedded applications can't go to a database, can only function on the data that it's receiving from the tag itself, and can control other devices, gates, things like that, based upon the data that it's reading. So you can have an embedded application. Host applications are running on your PCs or your servers, and which the data is passed from the reader through the middleware into your host application. The host application then processes the data. So two places you can put applications. Typically, you're going to use embedded or applications where you don't have access to a server, and all you need to do is act upon the data that you're actually reading from the tag. Okay, so the next thing we're going to talk about is, we will go through here, is we're going to talk about RF physics, and we're almost out of time, so I'm going to go quickly through this one. And we can stop whenever any of you have to drop off at 8. Go ahead. We'll keep going for a little while anyway. So the RF, radio frequency wave, RF wave that goes out of reader, is in the form of what's called a sine wave, or sinusoidal wave, in which case you have an electric component as well as a magnetic component. We're only dealing with the electric component in RFID. So we have the sine wave that goes out, is transmitted. The wave looks something like this. Now this happens to be, once again, for UHF 915 megahertz carrier wave, in which case you have 915 million oscillations per second. That's what megahertz mean, 950 megahertz. And all your antennas are sending out, tuned to only send out one frequency. So it's sending out this wave. We have two different ways that the data is coupled, or how data is, the readers are coupled to the tags. When we're dealing with low frequency and high frequency, there's my alarm for 8 o'clock. So we'll go for a little while. Anybody needs to go, obviously, can go in much more detail, obviously, during the class. So we're just trying to give you a little bit of jump start. But anyway, so load modulation near field, whereas far field uses backscatter, and UHF Class 1 Gen 2 ISO 18060 uses backscatter. And with backscatter, the reader is sending out a wave, that power, that wave hits the antenna gathers that power, does two things. One, it gathers the power, which powers the chip, and that same wave is reflected back to the reader, and that provides the two-way communication channel. So now the reader can talk to a given tag, that tag reflects the signal back. So then that's called backscatter or passive backscatter. So near field coupling, it's using a magnetic field. And for those of you that have worked back in school, and you had a battery, and you connected to a battery, you wrapped the wires around a nail and powered it, that created a magnet. This is that same concept, in which you have a magnetic field, and you look at when you put a coiled tag in a HF or LF tag into that magnetic field, it will power the chip and provide the connectivity. So that's what's called near field coupling. So it uses a magnetic field. Near field coupling or inductive coupling is another name you may hear for it. All right. Whereas in UHF, we're looking at the backscatter, which we just talked about, sends out a wave. The wave is reflected back, and the tag sends the data. The reader sends the commands to the tag responds with the data back on the reflected wave. It's called passive backscatter. All right, so another view of the same thing. It's a radio, basically, that's once again sending out a signal through the antenna. It's collected by the antenna on the tag, reflected back, passive backscatter. Now, this is an important slide. So, and then probably after this would be a good time to stop. But we have two units of measure in RFID. One is called a watt, one is called a decibel. A watt is exactly what you'd expect from it's a measurable unit of measure by definition. You have a 100-watt light bulb, you have a 50-watt light bulb, etc. So you can measure it, you can touch it, you can feel it. And the other unit of measure is a decibel. If we have a cable and we're putting power through a cable, the power at one end is going to be different than the power at the other, because you're going to lose some power through friction through going through the cable. So how do you measure that power in a cable going from the reader to the antenna in this case? And so they created a unit of measure called a decibel, which is the power out divided by the power in. And it's a log function. So it's a log function of the power out divided by the power in. And you notice it has a capital B on it. And that's for a decibel is dB. D means a tenth, and B is capitalized because Alexander Graham Bell is the person who invented it. So that's why it's called a bell. And a D just means a tenth of a bell, just so we don't have to put so many zeros down when we write it. But anyway, so two units of measure that are important to us. And by definition, 1 watt of power equals 30 decibels. Okay, so those are probably where we want to stop, because the rest gets very complicated, and it's going to take more time to discuss it. But anyway,
maybe
okay,
very quick, the dBm, the M, what does it stand for? Because I see different, I see dBi where it's
okay,
isotropic, or
that is correct. So you'll see a dBd, which is where the D stands for dipole.
Dipole, yeah.
Where they're using a dipole antenna. A dBi is where they're using an isotropic antenna. So on that's what you'll see there. You'll also see a C for, we didn't get into it here, but we will in the class. You have circular antennas, circular polarized antennas. You have linear polarized antennas. So you see a dB, a dBci, a dB, etc. So you'll see different letters tied to the end of that. Once again, it'll be isotropic or dipole. It'll be C or L, circular or linear. So yeah, those just describe the antenna that's being used for how they're setting up and measuring this power.
Yeah, but what does it mean that when it says dBm?
dBm.
Yeah, in the second bullet you have power. Now the second bullet.
dB is related to milliwatts.
Yeah,
related to milliwatts.
Yeah, right. So watts, if you look under relative to 1 milliwatt. So yeah, so it's decibel bell per milliwatt. Sorry about that.
Yeah. Okay. Thanks.
Okay, so we'll end it for today, and once again, this will be online shortly, so you can look at it and walk through these the slides and look at them again. give you something to get prepared for this material. And we will go through this obviously in more detail in the class. And you'll have a chance to, in the labs, to actually see what this means and how it works and touch it and feel it. So it will help give an understanding. But okay.
So there were a couple of questions which was on the chat, and I'll just take a quick moment to address those.
Sure.
Matt has asked, can the same access password be used for multiple tags? So answer is yes, you can actually have a common password. But remember that whenever a tag is Googling a tag, a reader is Googling a tag, it is only talking to one tag at the same time. Though it has the ability to talk very quickly, but it's actually talking to one tag. So it will be passing the same access password, asking the further memory banks wherever it is used.
Okay. Thank you.
All right. Then there is another question from Derek, like what kind of depth for RF physics and others is going to be. Now, this exam is sort of an entry-level exam. Institute is right now working on developing the second level, which is a professional level. Right now, it's internally getting tested for beta. And hopefully by RFID Journal, we are going to be opening it for the people who has already passed the exam at the associate level, for asking them to take a beta for professional level. So this exam is going to be more like a wide exam, or a, not a deep exam. So, the people are expected to know a wide variety of, there are a lot of topics in RFID, right, from LF, HF, related technologies. The idea is that the people should be able to aware of like what this technology means. In this use case, can I use this HF or LF or UHF or ZigBee, or what kind of BLE or what kind of technology is appropriate for this use case, and then go a little deeper. Now, in things like RF physics, now we may be like teaching a little more deeper than what is required. Remember, this training is not only meant for exam cram for the institute exam. This training is also meant to give you what actually, when you see a flyer of antennas or flyer of RFID reader, you should be able to correlate what these lingos means in the specification sheets. You should be able to get a fair idea on how much deep it's going to be. So short answer, it's not going to be like, it's not expected that you become an RF physicist while going through this training and attempting the exam. It's like more like a general RF knowledge, the terms, like how it relates to RFID, you should be able to easily correlate to. A common example is that when we go to customer side and we say, okay, now we are seeing a power of 30 dBm. Now, shall we reduce it to 27? And if we reduce it to 27, what does that actually mean? How much power it is? Is it like 10% down, or 50% down, or 80% down? What is 27 related to 30? Because it's a dB scale. So all these things actually has a real life practical usage also.
Yeah, just to restate that, we aren't trying to teach an exam at this course. What we're trying to do is make sure that you have a good, broad understanding of functions, features, and capabilities of RFID, so that, as Sanjay said, when you go on site or you're working with a client or a customer, you understand what's going on, as opposed to just knowing answers to questions. So we do go much deeper in the course to make sure that you have a good understanding of RFID, broad base, because that's the most important part, not just passing an exam. So we don't teach an exam here. We teach RFID. We teach all the material that's covered in the exam, plus quite a bit more, to make sure that when you do go on site, you have a good understanding of what to do, how to deal with issues, how to set things up, how to resolve problems. Much more information than you're going to need on the exam.
Okay. Another question on RFID tag samples. Yes, we will be providing some inlays and some tag samples as a part of student packet, as a part of student handout. In addition, when you go to the show floor, you're going to be meeting virtually a lot of tag vendors. and those vendors will have their own specific tags or inlays and the use cases what they promote for. So at the end of the show, with us, whatever the tag samples which we'll be giving, as well as the other show vendors, which will be like displaying as well as talking about their tag samples, you're going to be seeing a lot of tag samples. Now, with regard to custom design, now that's like a little bit of a borderline area. Now, there are some tag companies which has their general use cases. Now, whenever we talk about a custom, of course, the custom tag design can be done as many as you want. We really need to know what exactly you are looking from the performance, the read range, and form factor, and use case, etc. Before we talk about like what kind of custom design it is. RFID for You has helped a lot of companies, both in pharma as well as many others, for custom designing, and we'll be more than happy to discuss separately with you. All right, these are the questions which, okay.
I have another question.
Sure, of
please.
course.
So this is
Sure.
in regard to the exam slots. So there's an exam on the 11th and another exam on the 12th. I had saw earlier in the chat box that someone had asked a question about maybe taking it on the 11th in case they don't do so well, and they can take it again on the 12th. Is that recommended, or should we just pick the slot that works best for us?
I think you should pick up the slot that works best for you, okay? And that's always easier, based on your meetings, your schedule, your flight schedules, as well as how much time, if you really want to spend one day in the mornings or evenings. It's going to be a very busy day with all the conferences and all the meetings and all the things. So you should pick up whatever is most convenient to you. If you prepare well based on the webinars, based on the quizzes, based on the training, as well as going through the internet, RFID general site, and reviewing all the things, I think you'll be okay.
But we wouldn't really know how we did on the exam if we took it on the 11th and be able to decide if we took it again on the 12th, correct? Or would we know after the 11th?
Up till now, like the training institute has been manually grading it. This time we are planning to use some system, but I'm pretty sure because they do the curving and other things, I'm pretty sure that you'll not be able to know the results right then and there. I can check with the proctors and let you know specific, but based on my past experience, it will be the results will not be known then and there. It will take time because of the grading and because of the curving which institute use.
Thank you.
Okay, there was another question from Bob, and they like to know about inlay specifications and adherence of component adhesive. Yeah, these are all like custom component, and most of the inlay manufacturers, particularly, will be much more glad to work with you to find out the right adhesive for you, and as well as customization of it. We can discuss privately on what's the best approach to get a custom inlay. And there are a lot of reference designs available with the chip manufacturers also, and you can. Most of them are royalty free. You can really use them as you want to.
Yeah, and in addition to that, we have a booth on the floor there, so we will be manning that booth. So at any time during the show, you have any questions, come by and see us, talk to us. We'll be more than happy to talk to you about anything you have, and or walk around with you, to some of the vendors, and so that we're asking all the questions to make sure you get all the right questions. But anyway, so we're on the floor to assist you at any time something comes up, you have questions, come by and see us. More than happy to work with you and talk with you, and with other vendors. So come by and see us.
Okay, great. Thank you.
All right. So please feel free to ask any questions between now and Sunday. Sunday will be on site, and then looking forward to see you at about 7:30 on Tuesday. The training starts at 8 o'clock. So we are looking forward to see you.
Hey, see you then.
See you. Have a good day.
All right. Bye-bye.
Bye.